So let me start by thanking the organizers for putting this conference together and for a very kind invitation. I've been really enjoying this, and of course this is a marvelous place. And I'm very sorry that due to personal circumstances I will have to leave early. I'm very sorry to miss a lot of things that have to come. Anyway, this is in part joint work with various people, so I'm going to say this now because before I probably forget. So partly joined with Gary Redman, Haber, and then Rochna, and then I'm going to work with Viet, Dang, and Rochna. We'll briefly mention later. So, like some of the talks today is sort of quite different from the classical dynamics talks, but there are of course connections. So in particular due to the four-strand approach to dynamical systems, which then had many applications and extensions. So for example, the Dyatlov-Zworsky proof of the Julia-Tilly polyquot theorem, and many other things like Suji and many others. So there are connections, but this is more of a sort of quantum talk in a sense, although it's sort of classical from the wave equation perspective. So this is about so the headline in this Feynman propagator is about Lorentzian manifold. And so for today's purposes, this we mostly should think about asymptotically like Minkowski. And so Minkowski already came today. So Lorentzian, so say by in n dimensions, so it's in the signature, it doesn't matter which way, it's either one n minus 1 or n minus 1, 1. So you have a pointwise inner product, which is not positive definite, but has the signature or the signature on the tangent space. But in fact, many of these things, in particular this Feynman propagator business, works in other signatures as well. So let me just say right away, in any signature, I mean the Riemannian signature is what's not so interesting from this perspective, analytically, because it corresponds to elliptic problems. But all the other ones are interesting. So Peter Hintz already talked a bit about solving wave equations. So let me just recall that what is the usual way of solving wave equations. So it's the Cauchy problem, which goes back longer than Cauchy. So if I say anything negative about the Cauchy problem, don't blame Cauchy. Certainly not his fault. The typical way, so typical wave equation setup is that you have an initial surface. So this is a Lorentzian manifold. Say M, comma G, is that you have a Cauchy hypersurface, so let's put S, so this is your initial hypersurface. And then you're going to take the wave operator that corresponds to this box G. So say in the scalar setting, I just talk about scalar things, again, well, I will say something about more non-scalar things later on. So this is, right, it's just D star, but the adjoint is with respect to this metric, so dg star D. So that's our wave operator. And then you might want to solve Bugs GU. So let's solve the inhomogeneous equation. So Bugs GU is equal to F, so F is given. The Cauchy data. So U on S is something given, I don't know, phi0. And a normal derivative of u at S also given, so let's call it phi1. So V is a vector field transverse to S. All right, so that's the usual setup, and you always have low-cost solvability, it's always okay. It's a nice linear wave equation. And under global hyperbolicity, which you can phrase in different ways. So one good way to think about it, there is a global time function. Global time function. So under global hyperbolicity, you actually get global solutions. So that's the sort of classical way of phrasing so solving the wave equation, as one classically means by it. So this is sort of like the analog of the flow. So I mean, if you ignore this f, these two bits is like the analog of exponentiating a vector field. So this is actually equivalent to the inverting, in a way, the vector field or Lie derivative of the vector field or its spectral family. So this is equivalent to solving the forcing problems, where I can suppress this quotient hypersuppress somewhat. So for example, so let me just do this with a time function, t, and so this S will be and so here what I want to say is to solve, say, the future version forward in time. You want to solve box u is equal to f, where the support of f is in t bigger than t0, such that u is equal to 0 in t less than t0. So u is also supported in t bigger than t0. And so this would be the forward in time, or retarded solution operator. So u will be this box G, and so let's do it R inverse of F. So that's what it is. So I mean, so solving the quotient problem is equivalent to being able to solve this forward and the backward in time, and the backward in time or advanced problem. So the analogous thing would be box G A inverse. Okay, so there are two sort of standard inverses for the wave equation that correspond to the usual picture that's that warms the determinist's heart. You know, you specify initial conditions, and then you just solve, and the future is determined, so the past. But so it turns out that in many settings, and so I will talk about this asymptotically Minkowski-like settings. In many settings, there are two more inverses of box G that are natural. And so this will be the Feynman and the anti-Feynman. And so I will explain later how where this comes from in various contexts. And then this is something that will extend. So these, as I already mentioned, but let me just emphasize this. This also exists in other pseudo-Riemannian settings. So in general, pseudo-Riemannian settings. So, I mean, again, under some sort of geometric constraints. So this corresponds to ultra-hyperbolic problems, right? So this is where you look at things like I don't know, that's what it coordinates Vz1 squared plus Vz squared. This is a stereotypical ultra hyperbolic operator, k plus 1 squared Vzn squared. And so here we're k and n minus k are both at least 2. So this is neither Riemannian, so neither elliptic nor hyperbolic, neither Riemannian nor Lorentzian. And so of course for this, it's non-elliptic, so it sounds bad. The Cauchy problem is terrible, so that sounds bad. But I would argue that you shouldn't blame the operator, you should blame the Cauchy problem. So if you try to do something else, then maybe these, they will work perfectly nicely. Okay, so don't blame poor ultra hyperbolic operators. Okay, so in a vague sense, let me just say that sort of asymptotic Minkowski so I'm not going to define this, but one way to think about it, e.g. on Rn, so this doesn't actually require Rn, so it does not mean asymptotic to Minkowski, so more general. Asymptotic to Minkowski. And in fact, the underlying space can be quite different. So this is like asymptotic hyperbolic, for example, is usually not meant asymptotic to hyperbolic. But so for example, on Rn, this would be that in sort of standard, so you have standard coordinates now as dz, and then your metric in this coordinate gij. So this should satisfy estimates, it's just basically symbolic estimates, that you differentiate them a bunch of times. This thing should be less than constant time, well, depending on alpha, times z to the minus alpha, so symbol estimates. With some sort of asymptotic behavior restriction, which maybe I will say later. But so just to give a sort of rough idea, so this is sort of quite usual in geometric context, so say even in the Riemannian context, like asymptotically flat spacetime. So that's the sort of thing that's that you are looking at. Okay, so okay, so how do we describe these various? So actually, one point I want to emphasize that I really care about inverses, or at least almost inverses. So like I want to have, for example, a Fredholm theory for these sort of things. And so one important point is this Feynman, anti-Feynman inverses are very global. So, so one thing that one uses a lot for the wave equation usually is the finite speed of propagation, which amounts to that the advanced and retarded propagators are very local in nature. And this is really abnormal. I mean, one shouldn't think that this is a standard thing that should be happening. It's true, but it's not somehow true by systematic reasons once one is in a bigger world. Think of something that's more general than Lorentzian metrics. So for example, you want to be in this ultra hyperbolic world or something like that. So, or even, in fact, even the Riemannian world, like the elliptic equations, solutions for them are necessarily global. So if you want the unity of PDE, you are thinking like an algebraic geometer. The PDE is somehow a unified world, and then this is somehow the natural thing that one would expect, even though, of course, there can be coincidences, where sometimes things go bad. So they're necessarily global. And so correspondingly, a way that you'll be encoding these, so the inverses, various inverses are encoded by choices of function spaces. So, I mean, this is the analog of writing elliptic problems, say in bounded domains. You might impose boundary conditions, say Dirichlet boundary condition or Neumann boundary condition. So that's encoded by a choice of function spaces on which you are working. So it's a similar thing that you should be doing here. Now, what kind of encoding? So there are various ways of doing it, but the simplest recipe, in a sense, is an analog of what in the dynamical system setting happens in the work of Foer and Sjöstrand and then others. So I like to call these variable order rather than anisotropic Sobolev spaces for various reasons. For one thing, they're not necessarily anisotropic in the causal, so advanced retarded settings. So typically this would be some sort of variable order or anisotropic Sobolev spaces of some kind. And the choice of this variable order determines the inverse or almost inverse, let's say generalized inverse. So maybe looking at the Fredholm theory. Now, for example, I just think of the Minkowski or the assessment like the Minkowski settings. So one thing one can think about is just box G, where G is Minkowski or maybe or asymptotically Minkowski. But so there, in order to have a nice theory, so one thing that plays a key role in this, because it's not an elliptic operator, is, so let me just say this is certainly not elliptic in any sense. It's not even locally elliptic. So even if you want to ignore infinity, infinity is far away, let's pretend that it doesn't exist, which is very unwise because of the global consideration. But certainly even locally, it's not elliptic. So it's certainly not elliptic. And so the basic sort of non-elliptic thing that came up already a number of times, for example, in Stefan's talk in semi-classical setting. So what this implies is there's sort of propagation of singularities or regularities, the sort of usual word, but I just say propagation of estimates because A, that's how you prove it, and B, that's what matters for a Fredholm theory. So it's really in the phase space level. So along null geodesics in the phase space. So that's why I'm lifted. Or you might want to call them null characteristics. Or if you are Riemann, you might just want to call them by characteristics, since the non-null ones are irrelevant, and therefore one shouldn't even think of them, right? Anyway, so you have this propagation phenomena along null geodesics, and so one thing you need is a global structure for these. So the nicest things are the nicest situation, which certainly is true for Minkowski or perturbing Minkowski within this category. So nicest situation is sort of non-trapping. Non-trapping metrics, which, so I really mean something stronger than the obvious. So the obvious thing would be that the null geodesic escape to infinity. I really want some sort of generalized, so I hopefully get to draw some pictures later on. A generalized source sink structure at infinity. So I hope to compactify things at some point, and then infinity is not going to be so far away, so I can actually draw the picture. And so this is sort of analogous thing in this dynamical system picture. Is the dual stable and unstable bundles, again at infinity, playing a similar role in the fibers then. of the bundle. All right. So, okay, so didn't say. So e.g. that, you need some assumptions, but then what will happen is that the, so this bug G will be a Fredholm operator. This is a Fredholm operator on what might be called, so I put in parentheses weighted because they should be automatically understood. That's sort of selbstverständlich part. So on Sobolev spaces, B Sobolev spaces. And so here what this means is that the derivatives, so the weights are polynomial weights. So that's like z to some power L. And the derivatives are, well, let's say for z large, so we think of Minkowski, bigger than 1, say, that's large. So for the derivatives are with respect to linear vector field, so z I, so with respect to. Now, it turns out that for these spaces, in fact, so I was not so specific for good reason about what's variable here. So I have spaces like this. I don't know, S, let's call it HSL. So this means S derivatives. And I'm going to call it B. So this is Melrose's terminology, this B, and maybe it will show up in a little bit. And this is the decay corresponding to this. So these are, like, so you multiply by z to the L, and you still end up in the S space. So your S derivatives relative to L2. Anyway, so it turns out here that this L really, you have to, this is constant. But this S is a function. In principle, on let's call it the B co-sphere bundle of quantified space. So, okay, so I hope to. I'm going to switch to something else in a moment. So I'm not going to explain this very carefully. So this is my compactified Minkowski. So it's a compactified Rn, which I hope to explain. And then what this is like the relevant cotangent bundle, which is this. Subtract the zero section and quotient by dilations, right? So the usual picture of microlocal analysis is you're working at infinite frequencies, and to bring the infinity closer, you don't compactify because of some reason, at the various historic reasons. It's easier to think of group actions. So you subtract the zero sections and quotient out and think about homogeneous or conic things, right? Okay, so it's going to be a function on this. And what this function is supposed to do is that this S is monotone along the Hamilton flow. Let's call it H P flow, where P is the geometric function. So the squared length, quote unquote, of a covector. So it's monotone along this and satisfies inequalities at. So, okay, maybe I will draw a picture here, a small picture. So Minkowski, this compactified Rn, so what will this look like? What this will look like is, again, you will think of, maybe I should have a tiny bit more room. What will this compactified Rn look like? Well, what you're really compactifying is a vector space, right? So Minkowski is not Euclidean, right? So you shouldn't really think of metric structure. So what you're compactifying, finite dimensional vector space. So what you do is you, so I'm just going to write Rn, but don't think about this Rn. It's an abstract finite dimensional vector space. what you're doing is that you're gluing a sphere. And what's the sphere? The sphere you shouldn't think of as a metric sphere. It's really Rn minus the origin quotiented by dilations. So what this really is a transversal, a smooth transversal to the R plus orbit, the dilation orbit. Right? And so the dilation orbits look like this. So here's origin, and then here's the dilation orbits. And I'm going to draw a wiggly sphere. This is my sphere. And they're gluing this to infinity. Of course, it's easier to think about it just using a metric. So my compactified Rm will look like this. So this is my Rm bar. And so here are the dilation orbits. And so to make it concrete, I will use a polar coordinate expression. So I'm going to write, I'm going to put the variable here z. I'm going to write z as usual as say r times omega. Let's put on a metric to make it concrete. So r is the magnitude of z. Omega is then a unit sphere. So actually it would work with this transversal if you interpret this appropriately then. Anyway, so you do this, and then you introduce rho to be the reciprocal of r. And the point is now that you're going to glue in rho equals 0. Okay, so in other words, you're going to take, say, 0, 1 in rho across the sphere, and you identify this with, well, you glue in, and you open the open, is identified with 1 infinity in R across the sphere. And the identification is this rho is equal to 1 over R, the point in the sphere unchanged. So I make the R into a ball. And so this is my infinity now, and this compactification of Minkowski space. This is now my boundary. Okay, and so the nice thing then, from this perspective, is that what do my null geodesics do in Minkowski? And so so basically you want this analogous structure in the generalizations. What do the Minkowski null geodesics do? They're very nice because they are just 45-degree lines, just like in Peter's talk in the original RM picture before I compactified. And so what they will do is they will go from the light cone in the past. So I'm drawing this in a very low dimensional way. So let's call this, I don't know, S minus. Just the zero sphere happens to be disconnected, so it's 2 points normally disconnected. The future light cone, and this is what the null geodesics do. Things like this, or of course they could go backwards. Okay, and so the monotonicity is along the null. So again, you are really in phase space, so you're taking the cotangent bundle over this. Monotonicity is along this. Really, again, you should think about if you really want in a homogeneous degree 0 way. There yet we'll quantify the fibers of the cotangent bundle soon enough. And then there should be inequalities that are true. So in this picture you can see that the appropriate object above S minus and S plus will behave like sources and sinks normally, just like the stable and unstable dual bundles at infinity would behave in the dynamics system, dynamical system case. And so you should satisfy inequalities at this, let's put it, generalized sources sinks. And so so it's like less than a threshold at, say, at 1, bigger than the threshold at another. Okay, so that's so this choice of S is what will dictate which inverse you get. And so what's special about the so this is what happens when one doesn't give a slide talk, that one goes completely differently from what one was planning. I shouldn't ever use this. Let's go here.
The boundary is rho equals 0, right? The boundary.
Boundary is rho equals 0, yes.
So M bar is always Rn, or you can consider more general?
Pardon?
M bar is always Rn. I mean,
no,
M is always Rn, or you.
No, not necessarily.
Yeah.
But if you, not for the analytic setup, but once you start caring about the structure of the bicharacteristic flow, that can give restrictions.
You didn't. What is the source and the sink? Because this lives in cotangent.
In the cotangent model, yeah. So it's really the appropriately understood sort of conormal bundle, B conormal bundle. So this is really some sort of conormal bundle. So I mean, this is just the appropriate version of the conormal bundle. Here, spherical. And so they have two halves, and so at each you have sort of different possibilities. Okay, so what's so special about the Lorentzian case? So really there are only three different kinds of cases. There's the Riemannian, which is elliptic, so there's no null anything, right? So no zero length vectors. But what's special about the Lorentzian case relative to the pseudo-Riemannian, general pseudo-Riemannian, is that the sort of energy shell, so the set where p is equal to 0, so this total as a subset of phase space with the 0 section removed. So I don't know, you decide whether you like this B phase space or the tangent, cotangent space, or you think about just at a single point in the interior and then you forget about B's that don't matter. Zero section. The point is that these things is as two connected components. Right, so the light cone looks like, so this is really in the fiber of the cotangent bundle. So that would just standard bundle. Right, so this is what the zero looks like, and I'm removing really this, and so it's two connected components, as opposed to any other non-elliptic, non-Riemannian signature when it's connected. And so what happens is that that in each connected component, one can choose the let's put it the direction of monotonicity, so monotone increasing or decreasing. Of S independently. So meaning that in a single connected component, I can only decide that I'm always going along the Hamilton flow or that I'm always going against the Hamilton flow. Right? Those are the only two choices I can have. But if I have a number of connected components, I can make different choices. And now, once I phrase it this way, the rational person can do exactly two things. Namely, always go with the flow or always go against the flow. Right? So the choices as always increasing in the weak sense, but increasing along the flow. The HP flow, always, everywhere, in the characteristic set. In the okay, so this is the increase, and this should be the anti-Feynman, if I have my signs right. Or S is decreasing always. So this is the Feynman choice. And then there are the two unreasonable things I mean, why would anyone do this? Except that, of course, people have been doing the Cauchy problem for a long time. Right? The other one is that S is increasing in one and decreasing in the other component along the flow. So these are the causal, so in other words, advanced Feynman problems. I mean, Feynman, Fredholm problems, or problems, problems. And so, I mean, there are some restrictions that I'm going to now suppress because I want to get to some other things. But basically the point is up to some restrictions on L, up to some discrete, so that L shouldn't take a certain discrete set, restrictions should take place in a discrete set. On L is a Fredholm, O Fredholm, and under some extra assumptions on L, so that's the picture for box, and so this part is actually was joint work with Gerard Redman and Haber. So I meant to say about box itself, no more than about a slide's worth of things. But everything I said is actually useful for going that I wanted to talk more about, which was the spectral family. So that's box G minus lambda. So here this lambda is very much lower order than as a differential operator than box. So it's not even sub-principal, it's like sub-principal, right? So this is very much lower order. So from the perspective of the usual local behavior, so this is 2 orders below box, in 2 differential orders. And so for local theory, it's really irrelevant. Now, actually, let me just say, maybe it's either, well, you can think about this whole thing. So of course this, so local parametrics versions in this sort of setting or even more general settings go back to Duistermatt and Perlmutter. And so they were interested in this in part because of a question of Whiteman, because of QFT relevance. So Feynman anti-Feynman, of course, highly QFT relevant. So go back to Duistermatt and Perlmutter, but so they're very local. So this does not give a Fredholm theory. It is necessarily global in this case. And then let me just add here for at least, I mean, there are many people working on this, but it was the QFT, QFT connection was due to Radzikowski, who who translated the more usual in QFT Hadamard condition into this microlocal language. Anyway, so that's a fact aside. So back to the spectral family. So this is much lower order, so it's irrelevant in the locally, but of course globally it's not. So so in this case, the Fredholm theory. There is again a Fredholm theory. Actually, let me start with first lambda in R. Let's first think about lambda non-zero and real. So that's the analog of say Euclidean scattering theory. So Laplacian minus a real spectral parameter. Well, so positive in that case. So the Fredholm theory now is on put standard, but anisotropic, so there's that, or variable order. Oh, so maybe just say that, right? So here for the in the Minkowski setting for the causal propagator, you can just take this variable order, basically something along. It's not quite like a function of the standard time function, but something similar. So it can be a function just in the base manifold, so just on position space, and so hence it's not really anisotropic in that sense. Anyway, so on standard anisotropic variable order spaces. So standard meaning that the derivatives are dCj, and the weights are still polynomial. Like this. Let's call it R. And now, so my Sobolev space, so actually let me just use two different notations for this. So it might be HSR. So this is like when S and R are constant, this is the usual notation for a weighted Sobolev space on Rn. So that's exactly what it is. If you want to use like a geometric microeconomic analysis, so a la Mero's terminology, so the scattering Sobolev spaces. So you have these spaces like this. And so what will happen in this case is that it's actually the decay order. So again, this is the differential order. And this is the decay order. And so what will happen is that S can actually be constant. I mean, you can make it variable, it's irrelevant. You don't need to. S can be constant, and what's variable is R, a function. On, again, really the energy shell. So on the, I'm going to call it P equals 0, where P is now, you should think about it as the duometric function. So G inverse, this is a duometric function. Minus the spectral parameter, and it's really, it's really should be thought of as living at infinity. Okay, so this is the analogous thing to the Euclidean scattering theory. So where of course. So standard Laplacian minus lambda, where lambda is not positive. So standard scattering, this is asymptotic Euclidean. So of course an elliptic operator in the standard sense, so locally nothing happens, but at infinity exciting things happen. There's just a propagation at infinity, and then it's the decay order that should be variable. So it's again the same setup. With R, so S has to be irrelevant because it's an elliptic operator. So it's one can't even think of a reason why it should be potentially the variable that one can allow it. Even with reality problems you can. So here R is the important variable, and so what it has to do is the incoming outgoing conditions, right? So R has to be I didn't write down exactly the from which space to which space, but let's just say R is less than -1/2. Versus R is bigger than -1/2, but incoming and outgoing, whichever you want to go. This would be the backward, I guess. Let's go then radiuses. So okay, so there's an exactly analogous picture for the wave operator, and so you change the spaces. In some sense, of course, this is the natural. So if you are a category theoretician, then these scattering spaces are the natural category because that's what the operator or its spectral family is naturally in. So what was there, using this crazy vector field, this B vector field, is somehow abnormal, and really that happening because what happens is that actually I should just draw a picture. So back to, let's draw a proper phase space picture. Right, so the phase space is, let's just do a T star Rn, right? But if I draw T star, if I say T star Rn is an Rn cross an Rn star, so Z position zeta momentum, and we're going out very far away. So a better way to think about it is to think about it as a compactified version where I compactify separately in both variables. Something like that. So the picture we look at is, right, so this is a, okay, now I have dimensional limitations in drawing. This iron bar was a ball. This is another ball. It's a dual vector space, it's a vector space, so who cares? So it's a product of two balls, and I can only draw the product of two one-dimensional balls, meaning intervals. So here's my phase space. So that's for this. Okay, so that's my picture. And so what happens in this case is that it's not enough to think about what happens to develop a Fredholm theory. It's not enough to happen what happens as zeta goes to infinity, which of course fine for local theory. So if one is doing the dynamical system on a compact manifold, that sounds like that should be all right. Or whatever on compact, an elliptic problem on compact manifold, you should have to think about zeta going to infinity. But here you also have to think about z going to infinity. And so the way you should think is that the principal symbol of an operator lives, quote, on the boundary, so you have to be slightly careful in interpreting this, on the boundary of this compactified space, of compactified phase space. And so that's the reason, so that means everywhere here. So of course here, so this one might call, quote, fiber infinity, infinity in the fibers of the cotangent bundle. But there's also this thing, which is, you might call base infinity, because really at infinity in the underlying manifold. And so this P, the lambda enters is because of this. So here lambda is relevant. And this is a finite point in the fibers of the, okay, slightly rescale, whatever, cotangent bundle. Anyway, it's a finite point. So this is a primarily some finite number, lambda is some other finite number, and you're comparing it. Right? Okay, so it's this decay order that's variable, and then you have a completely similar analogous theory of Feynman, anti-Feynman, and causal problems. So let's write that down formally. So what I'm going to finish with is, and so this goes through in the your favorite, or if you wish, your enemy's favorite pseudo-Riemannian setting. Okay, so here I made lambda real. So let me say something about lambda not real. So what happens is lambda is complex, not real. So what happens is that things go pretty badly. And in the sense that if you make the right choice, everything works, but there's only one right choice. So you have four choices, and okay, and an abstract reason, you would say two are strongly preferable, the Feynman and the anti-Feynman. And two have long traditions, so we should respect them, the causal ones. But when lambda is not real, then it turns out that there's only one reasonable Fredholm setup, and it depends on the sign of, depending on sign of M lambda, either the Feynman or the anti-Feynman problem is actually going to be invertible. So that's the Fredholm. It's actually invertible. So, this is and so again on the same kind of spaces, same space, and in fact, you can let the m lambda go to 0. So if you let m lambda go to 0, you are in this real lambda setting. And in fact, if you let m lambda go to 0, this limit exists in the appropriate senses, actually very strong senses, exists and goes to the lambda real Feynman analogous anti-Feynman. That's what F bar uses. So really, when you think about non-real lambdas, there isn't really much of a choice. There's only one thing you can do, and so then you of course might wonder, well, if I can solve the Cauchy problem, so what goes wrong? Well, what goes wrong is that the Cauchy problem solution will typically be growing exponentially, and exponentially growing things don't exist in these weighted subalab spaces. You cannot solve the problem. No matter how hard you try, you cannot solve the problem. There doesn't exist a solution. So let me just say one thing about so this is sort of the slightly annoying part here is that these are inequalities for R. So they're modified if I add some sub-principal part, but so say if the operator is formally self-adjoint, this would really be inequalities. This corresponds to the Euclidean setting the incoming width. It's the optimal. And one thing you would want for self-adjointness, which I guess was in the title, so one to work with a target space, or with the domain, domain sitting inside R2, which would be this H 0, 0. And so that doesn't look so good in terms of this. So again, okay, let me just give a. So this is a question that goes back to that's something Derezinski asked me, and the whole setup was introduced to me at the summer school by the first person who asked the question was Christian Gerard, and then Derezinski asked this concrete question. So Derezinski and the student Simpson had the results in an ultrastatic setting, so under some rigid assumptions. And then since then, Nakamura and Taira have some results in some other settings. So there are a bunch of results in this sort of situation about self-adjointness. And so the thing is that you want to make this spaces a bit smaller to sit inside R2. And so what I did some years ago, not too many years ago, it was probably maybe 20, I forget now, was so to prove self-adjointness in this setting by a somewhat ad hoc argument. So let me just state that one can do it in a less ad hoc way. And
So you want to prove self-adjointness of the inverse?
of the operator. So the same as this box is self-adjoint. So that's basically amounts to a statement that box plus minus, or say box minus lambda for lambda non-real is invertible on appropriate spaces, and you have to come up with a single domain at the end for the operator, and this should be sitting inside L2. That's the and so just to finish, turns out that Bayer spaces more refined, very sophisticated spaces for this in lambda not 0. So it's good that I drew that picture because now I just drew another picture and then there it is, that's the space. So the underlying phase space, what you do is blow up the corner of this, what I had before, this Rn plus Rn star. So I only end up with a picture like this. And so let me just finish by saying why. And so now I will have three orders. So I don't know, this was R. I don't know, let's call it K, and this is S. And so the point, so why? So what's the dominant phenomenon for analyzing box minus lambda on this space when lambda is non-real? So again, this was the picture. Originally, you're looking at box minus lambda. So when lambda not real, so what happens is that here, like strictly in the interior, what you have is that this is actually an elliptic operator because of the imaginary part. Right? It's actually elliptic. Right? Im lambda is not 0. That means the principal symbol of this is just not 0, period. Okay, so of course here, including to the corner, but then in a suboptimal way, in that you have this restriction. Here it's the sort of propagation of box G dominates. Okay, so at the corner there's some fight, and the reason why this theorem worked all right with the Fredholm statement was because they were going in the, well, in principle fight, but they were going in the same direction. It's a real fight if you make the wrong choice. If you try to do anti-Feynman when lambda has an imaginary has the wrong sign, it's a fight and you lose. But if you give the right signs, you have two positive things. Adding them up, if you estimate the sum, you estimate each, so you're good. But it turns out if you just resolve the corner like this, so this would be some like quadratic scattering. So this would be Gaussian oscillations. That's what you're measuring. This is where the two phenomena are comparable. And the upshot is that you get, so the upshot is that you get some compatibility between S and R. And so I start with this. S and K. So like S and K are, satisfy some inequality, but both can be very large or very small. But R is arbitrary. And so in particular now you get that if you take a Schwartz input, apply this inverse, you get a Schwartz output, or you can go to tempered distributions, whatever, anything in between. So once you do this, it's super easy to write down the self-adjointness of box. The essential self-adjointness with domain is, say, Schwartz functions. Okay, and then what I mentioned, the ongoing work with Viet Dang and Michel Rochna is to extend these things to the Dirac case, where, or the tensorial version, where you can't really expect self-adjointness with respect to something useful. You have, of course, a form of self-adjointness, but it's useless because of the analysis rules. So you can't expect self-adjointness, but it shouldn't really matter. That's not the real point. The real point was this Fredholm property under appropriate spaces. You can then do functional calculus using contour integrals, etc. And then what we are hoping to do is to extend a result, a very nice result of Dang and Rochna on the spectral action principle, the Lorentzian version of the spectral action principle of Kohn and Shamsuddin. So thank you so much for your attention.
Do you expect normal
under maybe very strong assumptions. I mean, this is the analog of the Euclidean setting, right? So the Euclidean setting we need very strong assumptions. So I think the analog would work, but of course 0 is a serious problem in the.
Okay, maybe like I think in the anti-Lucifer there is a result of a student of Angela Osman using normal extension.
Yes. So for these things like ABS or de Sitter or hypoid space or things like that, it's not the direct translation between the spectral problems, and so they actually better behave. They sort of correspond to just properties of a straight box. So yeah, so you have better results for those things.
So maybe in the analytic case.
Yeah, I think under sort of a complex scaling version, for example, would definitely work. I mean, I'm almost definitely, since I didn't write it down.
It seems like what you're doing could work on the compact base as well, as long as your back characteristics escape to infinity. Or
In what sentence, sorry?
well, like if your manifold M is non-compact here, but you could assume that the manifold is compact, and that the bi-characteristics of the Hamiltonian flow escape to infinity.
Yeah, I mean, so the analysis setup is the same I mean, so you don't really need, like the Lorentzian geometry is really irrelevant thing. It's just that that's how you naturally have the unnatural Cauchy problem. And it's sort of very natural to start with that. And, but it turns out that as soon as you do anything really interesting, that's the unnatural problem, right? And some of the Feynman, anti-Feynman are more from an analysis perspective, really those are the ones that naturally arise.
Some questions? Here in these geometries, when you say non-trapping, you mean that all bi-characteristics hit some boundary, either the horizontal one or the vertical one?
So, I mean, in a sense of, yeah, so what I really want is this sort of stronger, like normal, generalized source sink picture. And yeah, that's what you really need for this. But then the precise way, right, so, and then what's variable then is affected by the some sort of normal linearization at these. And so what happens in the, for a box minus lambda, to say lambda real, is that the sort of vertical direction is neutral, while in this direction you have the source sink behavior. And so that's what dictates that the R should be the variable order. And so that has to satisfy contradictory inequalities if it were a constant at the sort of source and the sink. Or the alternative would be to second microlocalize. That would be the alternative way to do it. But then, once you start doing these things, it just becomes like this imaginary part lambda, and you're trying to do it more precisely, it just becomes a bit messy. But the lambda equals 0 setting is really a second microlocalization. That's the best way to think about it. Not that one pulls this B spaces out of the thin air.
Okay, no more questions? No? Okay, well, thanks, Andras, again.